Okay, so I'm going to start out with this slide that we left off with last, and that was just about the pH. Now we're moving on to titration curves, and we discussed basically that a titration is a standard solution or a standardized solution, usually in your burette, being mixed with some unknown solution, and you use an indicator to figure out when you've reached an equivalence point, which is just basically where we have the same amount of added moles of the titrant to whatever unknown we had in the titrand or the unknown solution below. And so that's the gist of everything that we'll look going forward. And what we're going to do is we're going to just sort of dissect these different titration curves of acids and bases. We're going to look at strong acid, strong base. We're going to look at weak acid, strong base, and weak base, strong acid. So we'll look at three different scenarios in the following slides and sort of discuss the sort of anatomy that we're seeing for the curves that we would generate in the titration curves. And there's calculations, different types of calculations for every regime that we're sort of in within a titration curve. And so this just illustrates you could use generate a titration curve using something like a pH meter and just taking points consecutively as you sort of add a little bit of volume of the titrant and generate a pH versus titrant volume curve. And this would be one means of generating a titration curve. There's certainly more, but this is probably the most common that we'll use in what we're discussing. Okay, so before we get into looking at the curves, let's just clear up some nomenclature to make sure we're all on the same page here. So if we are considering the equivalence point, I've thrown that around a few times, the equivalence point for a titration is just when we consider that we've added enough titrant to neutralize whatever analyte we have present. And that neutralization is sort of verbiage that you'd hear with an acid-base type titration. And so we basically know that the moles of titrant are equal to the moles present in an unknown solution, and we can figure out what the concentration of the unknown solution is at that time. Usually we have to also be considerate of the stoichiometry of the particular reaction we're looking at as well. So, but the important thing is we know the stoichiometry between them. We know how much moles of titrant we added. We can figure out how many moles of the analyte in the unknown solution is. And so, and this we can usually figure out before we start an acid-base type titration. We can estimate how much sodium hydroxide is going to be necessary to arrive at an equivalence point. And that can be just an important piece to doing an accurate titration. I don't know how many times I've done a titration and been incredibly, just infuriated at the fact that I've stepped over that equivalence point simply because I got impatient at the very end. But if you do a calculation before, sometimes it can save you some of that heartache and frustration of going a little bit too far because you know how to get maybe 80–90% in there and then just ease up on what you expect to be the equivalence point. So let's just take as an estimate we have 25 milliliters of solution, and we consider it to be roughly 0.15 molar of HCl for our titrant. Usually you might have a sense of where your unknown analyte sits at, and so we're titrating with 0.236 molar sodium hydroxide, and the question is how much volume of titrant is going to be necessary to reach the equivalence point. And so this is just a bit of stoichiometry, or just unit conversions rather. And so we end up with 25 milliliters of HCl, do the conversions to get it into liters. We end up figuring out we have that 0.15 molar. And notice we're starting with the volume of the HCl, not the volume of the sodium hydroxide here. And so that's because we're estimating how much sodium hydroxide we need to add. And so we basically convert that over to how many moles per liter, and then we know the stoichiometry is 1:1. And so now we're looking at moles of sodium hydroxide, and we use the molarity of the sodium hydroxide to figure out how many liters it's going to take to deliver that many moles. And so we end up with 16 milliliters roughly of sodium hydroxide are necessary to reach the equivalence point. So in that case, if I was doing a titration, I knew it was approximately at a 0.15 molar solution of HCl, I'd probably ease up around 14 or 13.5 milliliters of sodium hydroxide added, and just start easing in the amount I'm adding until I get to that equivalence point. So if we look at before the addition of any sodium hydroxide, so that's the first point. What's our pH when we start with 40 milliliters of 0.1 molar HCl? And again, we're titrating with 0.1 molar sodium hydroxide, but we haven't added any at that moment. And so we only have a strong acid present, and we know that it's at 0.1 molar. And so this becomes a relatively easy calculation. Remember, a strong acid is going to completely dissociate. And so the hydronium ion concentration is just 0.1 molar. And if we want to find the pH, it's just minus log of 0.1, and that yields a pH of 1.000 if we want to throw all the sig figs in there. So, okay, so the next point we're going to look at is before the equivalence point. So you notice the equivalence point is after we added 40 milliliters of sodium hydroxide, as indicated by the graph there. So anytime before that, if we're looking at figuring out what the pH of our solution is. And so the way that we're going to do that is we have to recognize that the net ionic equation for the reaction that we're doing is hydronium ion with hydroxide to yield water. And so we're just neutralizing some of the hydronium ion that's present because we're at a low pH, we have a lot of hydronium, we're adding hydroxide, we're just neutralizing it. And initially we have a lot of hydronium ion, so as you're adding hydroxide, you're not changing the pH too drastically because it's just eating up some of that hydronium, and so the pH stays pretty steady at first. And so one of the things that we will keep in mind as we keep going through this is if we have 40 milliliters of HCl and it's at 0.1 molar, then we can calculate that to be 4 times 10 to the minus 3 moles of hydrochloric acid. So that is the same as 4 times 10 to the minus 3 moles of hydronium ion present. So that's how much that we have to neutralize. And so let's just take the halfway point. Let's calculate the pH after 20 milliliters of 0.1 molar sodium hydroxide has been added. Keep in mind that this is a reaction that this neutralization reaction has a equilibrium constant of 10 to the 14, so it goes all the way to the products. No need for equilibria or anything else. If we react 1 mole, if we put 1 mole of hydroxide, then it will react with 1 mole of hydronium ion if it was present. And so first thing is if we're adding 20 milliliters to the 40 milliliters of HCl, we need to realize that our new volume is going to be 60 milliliters. We'll have to keep track of that as we're trying to calculate the pH at different values or different places on the curve. So 20 milliliters of sodium hydroxide at 0.1 molar is going to yield, after it reacts in a 1-to-1 ratio, it's going to yield 2 times 10 to the minus 3 moles of HCl reacted. So we will basically neutralize 2 times 10 to the minus 3 moles of HCl. So if we started with 4 times 10 to the minus 3 moles of HCl, we reacted 2 times 10 to the minus 3 moles of HCl, then we will be left with 2 times 10 to the minus 3 moles of HCl. So the hydronium ion concentration for this is going to be 2 times 10 to the minus 3 moles divided by the 0.06 or 60 milliliters of volume that we have. And that's going to leave me with a concentration of 3.33 times 10 to the minus 2 molar. If we want to calculate the pH, then it's just the minus log of that concentration, and so it leaves me at a value of 1.48. So that is how we get the concentration before the equivalence point with the strong acid, strong base. Just have to look at how much hydroxide we've added, see how much neutralized HCl we've neutralized, calculate a new concentration, and then figure out the pH. Okay, so now we're at the equivalence point. So at the equivalence point, we have neutralized all the acid with all the base. So the number of moles of acid or the number of moles of base added are the same as the number of moles of acid we initially had. So that means we've added, in that case, 4 times 10 to the minus 3 moles of hydroxide. And that means that we're now basically looking at where we have equal concentrations of both of those. And remember, when you neutralize a strong acid, strong base, you're just left with whatever spectator ions and water, and that's going to yield a pH of 7. So when we're dealing with a strong acid, strong base titration, the telltale that we're doing that type of titration and we don't have any weak acid or weak bases present is just that we have a pH of 7. Okay, so moving beyond the equivalence point, so once we get past that, now you've neutralized all the hydronium ion. Now you're just basically adding sodium hydroxide. That's all you're doing. You're just adding sodium hydroxide. So we could ask ourselves, what is the pH after adding 50 total milliliters of sodium hydroxide? And so we just go ahead and calculate how many moles of sodium hydroxide we've added, and that's just 5 times 10 to the minus 3. Keep in mind that we started with 4 times 10 to the minus 3 moles of HCl present. We reacted all of that. So now we have an excess of 1 times 10 to the minus 3 moles of sodium hydroxide. And how much solution are we in? Well, we added 50. We started with 40. So we're at 90 milliliters of solution. So from here we can calculate the concentration of sodium hydroxide. That leaves me with 1.11 times 10 to the minus 2 molar. And then from that, using our 10 to the minus 14 over that concentration of hydroxide, we can end up with 9 times 10 to the minus 13 molar for the hydronium ion concentration. And then, of course, figuring out the pH just as the minus log of that. And that gives me 12.04. So this is just a chart if you'd like to sort of check out what the pH is after different volumes of addition of the sodium hydroxide for this particular pH. This is basically what you would acquire if you were doing this calculation in a lab, and you'd be left to then plot the pH versus the volume of hydroxide that you've added. Other than that, I don't really have too much to say on that. Okay, so what we're looking at now is a weak acid, strong base titration. So below we have a titrand, which is just going to be the weak acid, and it's going to be 40 milliliters of 0.1 molar acetic acid. And what we're going to have as our titrant, or what is in the burette, we're going to have a 0.1 molar solution of sodium hydroxide. Before we add any of the sodium hydroxide, we're trying to figure out what the pH of the solution is. So we just start with a 0.1 molar solution of acetic acid. So we know the Ka for this particular weak acid is 1.8 times 10 to the minus 5. And so in order to calculate the hydronium ion concentration, it's going to be just the same approach we've done in the past for a weak acid, where we use an ice diagram in order to calculate the amount of hydronium ion present. And I didn't go through all the details of the calculation here, as we've done a lot of these at this point. And so you can appreciate that the X value that we would get from our ice diagram is going to be equivalent to our hydronium ion concentration, and that is going to be the equivalent to the square root of the initial concentration, being the 0.1 molar in this case, times the Ka. Doing that, we get a value of 1.34 times 10 to the minus 3 molar. In order to find the pH, we just have to do the negative log of that concentration, and I end up with a pH of 2.87 to start with. Another thing that we should take note of in this particular calculation, or this particular graph that we're going to be following along with as we look at the different points here, they also keep as a reference this red curve, which is just, as I'm highlighting now, just the strong acid, strong base titration. And they keep this blue curve, which is just our weak acid, strong base titration. And so we'll call attention to several points in that as we move along. So now what we want to take a look at is before the equivalence point. You can see 40 milliliters is where that's going to happen. And so any volume in between there, we're going to look specifically when we've added 15 milliliters of sodium hydroxide. And so we keep in mind the reaction that's occurring here. We have acetic acid reacting with hydroxide to form the acetate ion and water. So it's important first to make sure that we know how much of the sodium hydroxide we've added. We know that we've had 40 milliliters of 0.1 molar acetic acid, so it's the same as our previous problem, where we'll have 3 times 10 to the minus 3 moles of acetic acid present to start with. As far as the sodium hydroxide, that'll give us 1.5 times 10 to the minus 3 moles of sodium hydroxide that we've added after 15 milliliters, as you can see in the calculation just up above on the top right there. We can also calculate the pKa. We know the Ka of acetic acid is 1.8 times 10 to the minus 5, and so just plugging into that to the formula of negative log of that Ka, we end up with 4.74. So if we want to figure out the pH of the solution, then we know the hydroxide is actively neutralizing the amount of acetic acid that's present, and so it's probably best to just look at how much have we reacted with. And I used an ice diagram. You can use it for non-equilibrium type problems to just sort of neatly put everything together. And so if we look at this, we have the 4 times 10 to the minus 3 moles of acetic acid. And I can't remember if I said 3 or 4 times 10 to the minus 3. It's 4 times 10 to the minus 3 moles that we would have started with acetic acid. And then we have the 0.0015 moles, or 1.5 times 10 to the minus 3 moles of the hydroxide we've added. And since we know it's going to completion, then we know that we're basically just subtracting the amount of moles of sodium hydroxide that we had to start with. And so that's going to end up giving me 1.5 times 10 to the minus 3 moles of the acetate ion. And I'll be left with that 0.004 minus 0.0015 moles of the acetic acid. If we have weak acid and we have weak base present, then immediately what we should think is the Henderson-Hasselbalch equation is going to be the easiest way to determine the pH for this particular solution, and that's why I calculated the pKa just a second earlier. So we have the pH equals the pKa plus the log of A minus over HA. And so A minus is the 0.0015, and it goes on the numerator, and then 0.004 minus 0.0015 gives me 0.0025, and so that goes in the denominator as our amount of acid. And then we plug in the 4.74, and what we'll end up with is that 4.52 as the pH of our solution after we've added 15 milliliters of sodium hydroxide. The region that we are presently in when we're looking at that addition there is considered the buffer region. So you can see it indicated by this sort of region right here that I'm highlighting. And so this is the area in which we have a good buffer. We have enough weak acid, we have enough of the weak base that it's going to eat up any hydroxide or hydronium that we put in solution and result in a minor change in the pH of the solution. So we should always notice where that buffered region is, and so there it is for this particular species. It's where we have some weak acid and weak base. Another way that we can easily do the calculation for this, and something I utilize a lot if we're doing like analytical chemistry or something, is just basically look at the moles that we've added, and since we're adding hydroxide, we're adding moles of the acetate and we're subtracting moles of the acetic acid. And so it's effectively just the moles of the acetate plus whatever we've added. And then we could do moles of the acetic acid in the denominator minus the moles of hydroxide that we've added here. So that can be an easy way to do these type of calculations if you prefer that. Another sort of, oh yeah, I've already mentioned the buffer region thing, so just won't expand on that anymore. Okay, so let's look at the equivalence point and figuring out what the pH is in this particular titration. So that happens at 40 milliliters, and so we're looking at when we've added enough base to neutralize all that acetic acid. And if you remember back to the strong acid, strong base, the pH was 7 when we hit the equivalence point. That's not going to be the case here, as we've alluded to before, just because after you've neutralized all the acetic acid with the hydroxide, you're left with just acetate ion, and we know acetate ion is a weak base. So we should expect that the pH should be north of 7, or just in the basic region here. So determining the pH, we should write that equilibrium that we're looking at with just the acetate ion yielding some hydroxide and acetic acid. And we know Ka equals 1.8 times 10 to the minus 5 for acetic acid. So again, using our relationships there, we can figure out what the Kb is for the acetate ion. And so we're looking for the concentration of that acetate ion. And so this is nothing more than an ice diagram that we set up. And we know that if we were to figure out basically the moles of acetate ion in that solution, we started with 4 times 10 to the minus 3 moles of HA. We neutralized all of it. So we are left with 4 times 10 to the minus 3 moles of A minus, or the weak base, the acetate ion. And what we have to pay attention to is we've added 40 milliliters of hydroxide solution. We started with 40 milliliters, so now we have 80 milliliters of solution. And so if we look at that ratio or the concentration where we would be at, it's 5 times 10 to the minus 2 molar. And so if we take basically our ice diagram, we'd figure out that the X is equivalent to the hydroxide concentration, which is going to give us the square root of the initial concentration being 0.05 molar times Kb. That's going to yield 5.27 times 10 to the minus 6 molar. Just remember, don't take the negative log of this and assume it's the pH. I've seen a lot of students do that, and they're just jumping the gun. Remember, the pH is defined as the negative log of the hydronium concentration. We don't have the hydronium concentration here. We have the hydroxide. So we first have to relate it with using the 10 to the minus 14 over the hydroxide concentration to yield the hydronium ion concentration, which would give me 1.90 times 10 to the minus 9 molar. That will yield, when we do the negative log of it, the pH, which is 8.72. So that is as we expected, being a basic pH for the solution at the equivalence point. Okay, moving to the area beyond the equivalence point. So we've neutralized now all the acetic acid. And so after you're doing that, you're basically just adding hydroxide. That's the dominant form. You're just basically adding hydroxide. It doesn't have anything else to neutralize in the solution. So that's really going to be the dominant thing that provides any hydroxide ions and changes the pH of the solution. And so if we're adding a 0.1 molar solution of sodium hydroxide, that is going to approach 13 as we figure out what the pH of that is. It should give us a pH of 13. And so if we calculate the pH after adding 50 milliliters of sodium hydroxide, where excess hydroxide is just our primary source, 50 milliliters is going to give me 5 times 10 to the minus 3 moles of sodium hydroxide added. And so we know we had 4 times 10 to the minus 3 moles of acetic acid to start with. We've neutralized all of that, so we have an excess now of 1 times 10 to the minus 3 moles of hydroxide in what is 90 milliliters of solution at this point. We've added 50 of the sodium hydroxide. We started with 40, so we're at 90. This gives me a hydroxide concentration of 1 times 10 to the minus 3 moles over that 0.09 liters or 90 milliliters. And that's going to yield a concentration of 1.11 times 10 to the minus 2 molar. If I go ahead and figure out what the hydronium ion concentration is, I get 9 times 10 to the minus 13 molar. And if I go ahead and figure out what the pH is from that, I get 12.05. And so that's basically the anatomy of these weak acid, strong base titration curves, and we went through every single step for this particular titration. So before we move on to the next type of titration, we should discuss a few key features of this titration curve with the weak acid and strong base. And if we look on the curve, if we're looking for the minimum slope that we see in each of these titration curves, which are given for different types of Ka. So the one that we start with down here at the bottom of the strong acid that we see sort of here, that's obviously the strongest. And then as we move up further, we're getting weaker and weaker and weaker acids. And one thing that we should note here is that the minimum slope, or the halfway point to the equivalence point, is where the pH equals the pKa. And if you remember earlier when we were talking about buffers, we said that is the optimal portion where we have the best buffered solution. So we can estimate right here sort of being the best buffer for each one of these right here in the center. And so one other important thing that's good to note here is that if we look at the pH change, it's much smaller for the weak acids, or the weaker the acid, as we get to that sort of equivalence point. So notice if we look at, say, the purple versus the very top, that's a huge pH change. And then the green versus the top gets a little bit more gradual, right? And then as we move up to something like the blue, it's pretty small, and the red gets very, very small for the difference in pH that we see there. Notice that the pH at the equivalence point is 7 for the strong acid, strong base. And then as we move to weaker and weaker acids, we see that effectively the equivalence point moves further and further up the titration curve, or up the pH becomes a little bit more than 7. So let's take a look at a conceptual. So here's a clicker question, and we have in this particular problem we have a titration of 25 milliliters of 0.1 molar weak acid with 0.1 molar strong base, and it asks which point best represents the endpoint of the titration. So endpoint is another way of saying just equivalence point. We should see here that the equivalence point should be that value C here. We can recognize it as that steepest part of the curve. The other point that I haven't sort of mentioned too much, I think I did a little bit in one of our pre-labs, is that what you're looking for, and I'm going to try drawing this on here, so it's going to look horribly ugly because I'm doing it with a mouse. But the other way that we could do this is the equivalence point is an inflection point, which means that the curvature is sort of moving in, before we get to the equivalence point, it's moving in a counterclockwise fashion, so it's going in this direction. Now, after we get through that equivalence point, if we were to follow along with this curve, we see that the curvature, if we were to follow along, is going in a clockwise fashion. And so where that transition occurs is the equivalence point. And that's just another mathematical way that we could understand where the equivalence point sits if we want to. So it says in the titration of 25 milliliters of 0.1 molar weak acid with 0.1 molar strong base, which point represents the buffer region of the titration? One thing we said about that buffer region was the fact that the buffer region occurs where we have the sort of minimum slope, and we also have some weak acid and weak base present. So if we think about D, it's got a pretty small slope, but at the same time there is only weak base present, not any weak acid. We've neutralized all that. The only place that has a lot of weak acid and weak base is going to be at point A. So point A actually represents where the buffer region of the titration is. Okay, so now we move on to our last type of titration. So we've looked at strong base, strong acid. We've looked at weak acid, strong base, and now we move to weak base, strong acid types calculations. And you'll notice that the first thing about the titration curve you're looking at is that it looks a bit flipped. And so our buffer region is going to be towards the top of the pH, and our equivalence point is going to be at a different place as well. So we'll discuss all those features. What we're going to look at for this titration is we're going to look at just ammonia, a weak base. We're going to consider a 40 milliliter solution of 0.1 molar ammonia being titrated with 0.1 molar HCl. Before the addition of any HCl, we're just looking at a weak base in water. And so a Kb is 1.8 times 10 to the minus 5. We'd set up an ice diagram. We'd end up with X equals the hydroxide concentration, which is equal to the square root of the initial concentration times Kb. That's going to end up giving us a concentration for the hydroxide of 1.34 times 10 to the minus 3 molar. If we look at calculating the hydronium ion concentration from that, we end up with 7.45 times 10 to the minus 12 molar. And if we look at the pH, we end up with 11.13. So, okay, so now we want to look at before the equivalence point. So that's going to be anywhere before 40 milliliters of HCl has been added. I'm going to take as an example, I'll just say let's add 30 milliliters of the 0.1 molar HCl. We know the reaction is HCl plus ammonia to give us the ammonium and the chloride. Chloride's just a spectator ion there. So I'm not going to use the ice diagram on this particular problem. You don't have to use that. I'm doing it in just sort of a different way, and if you prefer this over using the ice diagram for this reaction, that's perfectly fine. Whatever suits you best. And so we have 30 milliliters of the HCl being added. We can figure out from our stoichiometry how much of the ammonium ion that we'll create. So just using the concentration and then using the stoichiometry, we end up with 3 times 10 to the minus 3 moles of ammonium ion that is created when we have neutralized a portion of that ammonia. So if we started with 4 times 10 to the minus 3 moles of ammonia, we've basically neutralized 3 times 10 to the minus 3. We are left with only 1 times 10 to the minus 3 moles of ammonia in the solution. We need to figure out what the pKa is in order to plug it into the Henderson-Hasselbalch equation. Usually if you start with something like a weak base, you're given the equilibrium for the base, equilibrium constant for the base, or Kb. So in this case, it's 1.8 times 10 to the minus 5. Using 10 to the minus 14 over that value, we can figure out that the Ka is 5.56 times 10 to the minus 10, which then when we look at what the pKa is, yields 9.26. The pH then, using the Henderson-Hasselbalch equation, is 9.26 plus the log of the ratio of the weak base or the weak acid, which is 1 times 10 to the minus 3 over 3 times 10 to the minus 3. That yields a pH of 8.78. And so the other thing I just wanted to point out is notice that the buffer region is up top now. It's not in the bottom part of the curve, because in this particular solution, that's where you're going to have the presence of weak acid and weak base. So now, we're now all the way over to the equivalence point, and we want to figure out what the pH will be of this solution. So at the equivalence point, we know we've reacted all the initial NH3, and it's been neutralized, and all that remains is ammonium, or the NH4+. So we're trying to figure out what the pH of that solution is. The solution has 4 times 10 to the minus 3 moles of NH4+, but we're no longer in 40 milliliters of solution. We've added 40 milliliters of the hydroxide, sorry, the HCl. This yields 80 milliliters of solution. So if we want to figure out what our new concentration is, it's just the 4 times 10 to the minus 3 moles over the 0.08 or 80 milliliters. That's going to yield 5 times 10 to the minus 2 molar of NH4+. If we want to figure out now what the pH is, this is just going to be using the ice diagram, and as we mentioned before, that X is going to equal hydronium ion concentration. We solve for that hydronium ion concentration. It ends up with 5.27 times 10 to the minus 6 molar. Doing the negative log of that, we end up with a pH of 5.28. Notice that this is south or less than pH of 7, so we're in the acidic region now. When we had a weak acid to start, we ended up with a equivalence point that was north of a pH of 7, and when we are dealing with a weak base, we're going to end up with a pH that is south of 7 when we're at the equivalence point. So now looking at beyond the equivalence point, calculating what the pH is, we're just adding a hydronium ion at this point, just like in the previous problem. Once we were past it, we were just adding hydroxide. So if we're looking at figuring out what the pH is after adding 50 milliliters of acid, we know that 50 milliliters of this solution of the HCl is going to yield 5 times 10 to the minus 3 moles of HCl. We started with 4 times 10 to the minus 3 moles of ammonia. This means we've reacted 4 of the HCl, and we're left with just 1 times 10 to the minus 3 moles of HCl in excess that are just sitting in the solution. We've added 50 milliliters of HCl to the 40 milliliters that was initially there, so we're left with 90 milliliters of solution. To figure out the concentration will be just the 1 times 10 to the minus 3 over the 90 milliliters, or 0.09 liters, yielding us 1.1 times 10 to the minus 2 molar. We want to figure out the pH, just the negative log of that, and we end up with a pH of 1.95. So the plot to the right represents what? That's what it wants us to ask. And I would say probably the best way of doing this is maybe just figure out where you think that equivalence point is. And I think probably where this particular dot is a good estimate right here. That appears at about a pH of 9. So which one do you think that looks like? Before we even look at their choices there. We just did a weak base with a strong acid, and our pH ended up for the equivalence point being less than 7 in the acidic region. We saw with a strong acid, strong base, we ended up with a pH of 7. And we know when we do a weak acid with a strong base, we end up with a pH at the equivalence point, because you're just left with a weak base, of something that is higher than 7. So in this one, I would expect it to be a weak base, a weak acid with a strong base. And so if I look at my choices here, the one that seems to fit the bill is going to be number C, or not number C, but letter C. And that's going to work for this particular problem. Last thing is, we won't cover in much detail. We'll leave it to analytical chemistry if you decide to take that in the future. Polyprotic acid and a strong base. And what happens when we have a polyprotic acid is that you're going to have numerous equivalence points, because you're first neutralizing, say that first, maybe start with H2A. The first one's going to be an equivalence point where you're all now at HA minus, and the second one's going to be an equivalence point where you're all at A minus, or A2 minus rather. And so you're going to have multiple equivalence points, and you'll have multiple buffer regions as well. And so that's something worth noting for polyprotic acids.